Okay, today we're going to look at first the 1990 M3. Okay, so first of all, I'm going to look at the picture. Now, a lot of times when they have a picture, they try to scare you because up until this point, all the problems we've been doing have been horizontal springs with blocks moving horizontally, and this one is vertical. Okay, so the first thing we're going to do is whenever we see a spring like this, the first thing we're going to do is we're going to say to ourselves, what do we know about springs? Okay, we have Hooke's law, F is equal to minus kx. We have the period of a spring, T is equal to 2 pi times the square root of m over k. And then we know that the potential energy stored in a spring, U sub F is equal to 1/2 kx squared. So no matter what, whenever you see a spring in the back of your head, you should be thinking about these three things. Okay? Not like, I have no idea what to do. Now, we're not just plugging numbers in. Whenever we have problems, we're going to think about it holistically, what's happening in the problem. So when we look at this one, it says a 5 kilogram mass block is fastened to a vertical spring that has a spring constant of 1,000 newtons per meter. A 3 kilogram block rests on top of the 5 kilogram block as shown. So part A says when the blocks are at rest, how much is the string compressed from its original length? So what I'm going to do is I am going to write down first my given. Okay, so they tell me that one block, the mass is 5 kilograms. The other one is 3 kilograms. Okay, and they tell me the spring constant is 1,000 newtons per meter. Okay, so for part A, we know that at rest, the weight of the two blocks compress the spring, so which means we have to add them together. And of course, you don't have to write that. All right. So what we're going to do is we're going to use Hooke's law, and we're going to say that F is equal to minus kx. We're going to rearrange this equation, and we're going to solve for x. So x is going to be equal to minus F over x. So it's going to be minus mg, or I don't have to put that minus. If I put g as negative, it comes out the same over k. When I substitute in my values, negative 3 plus 5 times 9.8, that's why I put that negative here, over 1,000. Now remember, on FRQs, you always want to write all your units, because even today, once in a while, what they'll do is on a 15-point FRQ, the last point they might say, oh, if you put all your units for all your answers consistently throughout, they'll give you an extra point. Well, an extra point on an FRQ can be the difference between a 4 and a 5. So you want to always make sure you write down your units. Remember, in physics, you have a foolproof way to check your work, because when you carry your units through and cancel them, it checks your work. Now, when I do this on the calculator, I'm going to get 0.0784, which for significant figures we'll say is 0.8 meters. Now, if I wanted to check my units, in the numerator I have meters per second squared, and in the denominator I have a newton, which is a kilogram meter per second squared, divided by a meter. So if I work all that out, I would have meters per second squared divided by all of this. So when I start canceling things, I should get a meter. Oh, I forgot the kilogram there. Whoops. I was like, why isn't my kilogram canceling? So then we see that 1 over a meter is meter, so I end up with a meter, which is the correct unit. See, I forgot to put that kilogram. So again, going through with your units, just, if you have time, because when you carry through your units, it's a foolproof way to check your work. All right, now let's look at part B. Part B says the blocks are now pushed down and released so they oscillate. Okay, determine the frequency. So there's more than one way to do it. First, we know that frequency is 1 over the period. And right here, I put the period. So what I could do is I could substitute in I could write down the formula equation for the period of a mass on a spring, calculate the period, and then say F is equal to 1 over T. Or I could just say F is equal to 1 over 2 pi times the square root of K over M, because frequency is the reciprocal of period. Does it matter which way I do it? Absolutely not. You're going to get the same answer. So do it the first way that comes to you. So 1 over 2 pi times the square root of 1,000 newtons per meter over 8 kilograms. So when I do all the math, this comes out to be 1.8. And remember, this is like oscillations or vibrations per second, which is a hertz. Because whatever the object is doing, it's oscillating, it's vibrating. The word in the numerator just describes what the object is doing, and the actual unit is 1 over a second, which is a hertz. For part C, it says, determine the magnitude of the maximum acceleration that the blocks can attain and still remain contact at all times. There's more than one way to do this. I looked at the rubrics, and they had a way of describing it in words, but I wouldn't do it in words just because I like to calculate things. So if I am going to, so again, if the spring pulls down the 5 kilogram block downward, and A is greater than G, then the 5 kilogram block will move faster than the 3 kilogram block can fall, and they lose contact. But that's not the way I would do it. I would do it mathematically. So what I would do is I would say, okay, if they lose contact, the normal force is 0. And then I'm just going to do what I did all before. I'm going to say, okay, let me write my sign convention. I'm going to sum forces in the vertical direction. So I'm not saying what my mass is. I'm just arbitrarily saying mass. So mg minus F of n is equal to ma. I'm applying Newton's second law in the vertical direction. Now, if this normal force is 0, mg is equal to ma. The masses cancel, and I didn't even say what the m was, you know, whether it was whatever. So you see that g is equal to a. So the answer there is that a max, because it says find the maximum acceleration, is equal to g, which is 9.8 meters per second squared. Part D says, how far can the spring be compressed beyond the compression part? So remember, the block was like this. So now it's going to be compressed a certain distance here. Once it starts oscillating in simple harmonic motion, this now becomes the equilibrium point. So now it's going to oscillate like this in simple harmonic motion. Okay? So it says, how far can the spring be compressed beyond the compression point without causing the blocks to exceed the acceleration? So the key here is that, and let me just move this up. The key to this part is that the maximum acceleration occurs at the extremes of motion. Well, those extremes, when you think about it, so this was pushed down, this is my new equilibrium, this is going to go back and forth, so the extremes are just going to be the amplitude from the equilibrium. Okay, so it's going to be the positive and it's going to be the negative. So basically what we're solving for x is going to be the amplitude. So if I use Hooke's law again and I say F is equal to minus kx, and I say x is equal to negative f over x, this is actually the amplitude. So negative f over x, so negative, negative mg over 1,000, and I'll substitute in basically 8 times 9.8 over 1,000. So when I do all this, the amplitude is 0.078 meters. Part E says determine the maximum speed. So I want to find speed. So I know the speed is going to be v. So now for a second I'm going to say, what am I going to do? So if I conceptualize this, remember, this is moving. It's oscillating here. So from here to here, I would do the bottom amplitude here. From here to here, I have a change in height. Whenever I have a change of height, I'm going to use conservation of energy. So I'm going to do the energy from equilibrium to this maximum amplitude here. So I'm going to do conservation of energy. And when I do conservation of energy, I'm going to say, okay, the total conservation of energy says basically, the potential energy, I can say the potential energy at equilibrium plus the kinetic energy at equilibrium is equal to the potential energy at the maximum displacement, which would be A at the bottom, plus the kinetic energy at the amplitude at the bottom. And you don't have to use like these subscripts and stuff. You're just going to say these are the 2 points I'm going to do it. Well, at equilibrium, the potential energy at the spring is 0. Okay? Plus here, the kinetic energy at equilibrium, that's Kmax, which is going to be 1/2 m Vmax squared, which is what we're finding. And that's going to be equal to the kinetic energy, which is 1/2 kx squared, but in this case it's going to be the amplitude that we just found. So it's 1/2 ka squared plus this, which is 0. Because remember that at the kinetic energy is 0 at the maximum displacement at the amplitude. So now I'm just going to do some basic algebra. So I want to solve for Vmax. All right, well, first of all, I can get rid of these 1/2s. All right, so now I have m Vmax squared is equal to Ka squared. So I'm just going to rearrange the equation to solve for Vmax. So you can do it slow. You can say Vmax squared is equal to Ka squared over m, and then I just take the square root of both sides. So I have Vmax is equal to the square root of Ka squared. And if you call this x, a, we know again that the displacement, the maximum displacement is the amplitude, divided by m. If this were an FRQ and they want it all in terms of variables, make sure you use the variables that they ask. So if it says a or it says x, make sure you do the one that they're asking for. So now we have 1,000 newtons per meter divided times 0.078 squared divided by 8 kilograms. So when we do the math on this, Vmax comes out to be 0.87 meters per second.